Welcome to the deep dive. Today we're focusing on something that, on the surface, sounds pretty utilitarian: perforated metal sheets.
Right.
But it turns out there's this surprisingly complex world behind them. We're going to use a company called Fine Perforators, an Indian manufacturer founded way back in 1969, as our guide.
And it's a good guide because, at its simplest, a perforated sheet is, well, it's just a material, usually metal, that's been punched with holes.
But it's so much more than that.
Oh, absolutely. The word simple really doesn't do justice to the engineering that goes into it.
And that engineering has to be world-class. I mean, the first thing I noticed was their credentials. They're ISO 9001.2015 certified.
Which is the international seal of approval for quality management. You basically need that to play on the global stage.
And they are. These products are going everywhere. We're talking Brazil, Dubai, Mexico, the Philippines, with a 99% on-time delivery record. That's serious.
It has to be. That global reach and what these sheets are actually used for means the precision has to be just. Exact. We're not talking about just stamping holes in metal.
What kind of precision are we talking about?
Well, think about the extremes. The thickness can go from a super delicate 0.2 millimeters, almost like a heavy foil,
Wow.
all the way up to a heavy-duty 12 millimeter plate.
Okay, and the holes?
The hole sizes are just as varied. You can have a tiny 0.5 millimeter pinprick or a huge 100 millimeter opening.
But the number that really stood out to me was the tolerance. It says here, dimensional checks are guided to plus or minus 0.05 millimeters where feasible. 50 microns.
Yes.
Why does that matter so much? I mean, it's a sheet of metal.
Because that's the difference between something that works and something that fails catastrophically. If you're using it for, say, high-grade chemical filtration, that tiny tolerance stops unwanted particles from getting through.
So it guarantees purity.
It guarantees purity, safety, and performance. Getting that right every single time is completely non-negotiable.
And it's not just round holes, is it? I was seeing all kinds of shapes.
No, not at all. You have square, hexagonal, slotted patterns for, directional airflow or drainage.
And then there are the custom ones, triangles, diamonds, that seem to be more for design, for aesthetics.
And every single one of those patterns links directly back to the material science. The performance begins with the alloy. Sure, they handle the basics like stainless steel, aluminum, brass.
The usual suspect.
Right. But they also work with specialty stuff. Alloy steels, titanium, bronze, and it's all about the trade-off. You might pick stainless steel for a food-grade application because it's hygienic.
And corrosion resistant.
Exactly. But for something under heavy mechanical stress, you might need an alloy steel for its raw rigidity. The material has to be perfectly suited for its job.
Which brings us to where you actually see this stuff in the real world. It seems to have this weird duality, right? It can be heavy-duty industrial or
incredibly elegant, architecturally beautiful.
Okay, so give me an industrial example.
Food and pharma. They use stainless steel for sieves and screens, but the key is that the edges have to be burr-free.
What's a burr?
It's that tiny, sharp little ridge left over after punching the hole. A burr can catch bacteria and contaminants. It makes proper cleaning impossible. So getting rid of it is essential.
So that's the finesse side.
Yeah.
What about the brute force end?
Mining and aggregates. Think massive, thick sheets, maybe those 12 millimeter ones being used to sort and dewater crushed rock. They are under constant, enormous mechanical strain. Strength is everything there.
And then the aesthetic side.
That's where architects get involved. They use them for building facades, for partitions, ceilings. But the coolest application, I think, is in acoustics.
For sound.
Yeah. In a recording studio or an auditorium, the precise size and spacing of the holes can be engineered to absorb or disperse sound waves. It becomes a tool for sound control.
So if you're the one trying to source this stuff, what's the main takeaway?
It's that every single detail matters. The material you pick, the size of the hole, the pattern, the finish. It all has to be driven by the final purpose.
You have to know exactly what you need it to do, whether that's resisting corrosion or withstanding impact.
Which leads to a final thought, really. We've been talking about 0.05 millimeter accuracy in products shipped to places like Indonesia. These things have to survive weeks on a container ship.
Through humidity, temperature changes, custom.
Exactly. So that makes you wonder, doesn't it? What kind of material science has to go into the packaging, into the crates with their moisture protection and special edge guards, just to make sure the perfectly engineered product arrives, well, perfectly engineered.
The journey itself is another engineering problem to solve.
It's the final critical piece of the puzzle.